Now that we have the overview of resonance under our belts, what we need next is to be able to look at a structure and answer the question, can I draw resonance for this structure? And if so, what can I draw? So what that means is learning a set of patterns that we can recognize within various structures. So we're going to start with a pattern that we've already seen. It's the one that we used in formaldehyde. So when you have a double or a triple bond between two elements where they have different electronegativities, you can always move electrons toward the element that's more electronegative. Now, before we start drawing some examples of this, for this pattern and all the patterns that we're going to talk about, what we say about double bonds also applies to triple bonds. So any of these moves, any of these patterns that I'm going to show you, where I show you a double bond as the example, or within the example, could also be a triple bond, and the same pattern is going to apply. We're just going to focus more on the double bonds because you're more likely to see those more frequently, but it's true for both. Okay, so two atoms in a double or a triple bond, one's more electronegative than the other. We'll use the pattern that we used with formaldehyde. Now we have at this point drawn, by my count, formaldehyde about 47,318 times. So let's draw somebody else. This is acetone. And so we can do with acetone exactly what we did with formaldehyde, which is to start an arrow at the double bond and point to the oxygen. Then we draw the double-headed arrow to reflect the fact that the next structure is going to be another resonance contributor. And remember that the result of that move, the arrow started at a pair of electrons in the double bond, and we point with the arrow to where those electrons end up in the next structure that we draw. So those electrons have been pulled out of the double bond, and now they're a lone pair. That gives the oxygen a negative charge and the carbon a positive charge. Let's do some more of these just to get some practice drawing structures and becoming comfortable with the pattern. So here's a ketone. Same idea. So you can do this literally for any carbonyl compound. Here's an example that involves a triple bond. Does anybody remember what is the name of that functional group? If you said nitrile, you are absolutely correct. And so we have a multiple bond between two atoms that have different electronegativities. And so we can do what we did with the carbonyl group. That is, start an arrow at the triple bond and point to nitrogen. The double-headed arrow, that is, talking about this guy right here, the arrow that has two barbs at the end, shows that we're moving a pair of electrons out of that triple bond. And placing them on the nitrogen. That gives the nitrogen a negative charge and the carbon a positive charge. Now, speaking of charge, let's do one more example. Like this. So it involves an ion. There's a charge already on that oxygen. Do we care? We don't. Okay? All we care about is the fact that there's a multiple bond between two atoms that have different electronegativities. Pull a pair of electrons out of the double bond, put them onto the oxygen. Now what that's going to do is satisfy the positive charge on the oxygen, but we moved electrons away from the carbon. So that will have a positive charge. So pattern recognition is what we're after. So let's look at what are called allylic and benzylic systems. We're going to start with allyl cations, or the allyl group. So first of all, here's an allyl group. So an allyl group involves 3 carbons with a double bond and a single bond. Now, as you can imagine, that's probably going to be part of a more complicated structure. So this is going to be a little piece within a more elaborate structure. The carbon that's not involved in the double bond, so the one that's attached to one of the double bond carbons, is called the allylic carbon or the allylic position. So this is an allylic carbon, and attached to it are allylic hydrogens. Okay, so let's look at an example over here. So here's a molecule that has a double bond in it. Any carbon that's directly attached to a double bond carbon is an allylic carbon. So in this structure, we have these 3. These are all allylic. So the highlighted carbons are allylic carbons. The benzylic position, or the benzylic carbon, is similar. So in a benzylic position, you have a benzene ring and a carbon directly attached to it. Is called a benzylic carbon. Any hydrogens attached to that carbon would also be called benzylic hydrogens. And I had the label benzene here, but that's not benzene. It's benzene with a methyl group attached to it. So that is a typo. This is actually toluene. So that's terrible, but we'll probably be able to survive that. Okay, so we're going to look at the allyl systems first. System just means a collection of atoms. So it could be a molecule, an ion, it could be a part of a molecule. So we're going to look at allyl systems. Those are things, chemical species that contain allyl groups. We're going to start with a cation. So an allyl cation is something called a carbocation, which we touched on very, very briefly a little while ago. That's a structure that has a carbon with a positive charge. It's going to show us generally what to do if we have a double bond next to a positive charge. So let's start. I'm going to draw the simplest allyl cation possible. So positive charge at the allylic position, like so. So we're going to draw these things with the full Lewis structure first, draw the resonance arrows, understand what's happening there, and then we're going to translate this to the skeletal formula or format so that we can learn how to draw both ways. So in this case, here's the pattern you're looking at, a double bond next to an atom with a positive charge. You're going to start an arrow at the double bond and point to this bond right here. The resulting structure, notice again, one of the tenets of resonance, all the atoms are in the same places. The resulting structure looks like this. Now, if we were to repeat this exercise using the skeletal format, we could do so in the following way. Now, one of the things that you're going to need to become aware of is when you have a carbon in a structure that's drawn in the skeletal format, how do you tell how many, and it has a charge, it has a charge, positive or negative. How do you tell how many hydrogens are attached to that? Okay, so we're going to talk about that in just a second, but let me finish this part first. So in this case, if we were to assess these two structures and how much or how little each one contributes to the resonance hybrid, do we have a major contributor and a minor contributor here? The answer here would be no, we don't. There's not a major and a minor. In fact, these two are contributing exactly the same to the hybrid. So we would call these equivalent resonance contributors. They have exactly the same features. In terms of charge and what type of atom the charge is placed on, the presence of the double bond, and so on. And in this case, they contribute equally to the hybrid. However, we cannot say that they are the same. So they're not the same structure. Now, that might be confusing because many of you are going to look at the structure on the right and say, well, if I just move that around or maybe even just flip it over, it's exactly the same as the one on the left. Okay, well, that's the point, is that they're equivalent contributors. However, the positive charge is shared between the carbon on the left and the carbon on the right in each structure. So in many cases, it's possible to draw the hybrid as a single structure or a single entity. We're not going to do very much of that, if any of that, in our course. I'd rather that you had the practice drawing the individual contributors, assessing the individual contributors, and most importantly, drawing these curved arrows correctly. But in this case, for example, we could draw the hybrid like this. So the dashed line shows that the electrons are being delocalized across those three carbon atoms, and the positive charge in the middle of that is showing that the carbon atoms are sharing the positive charge. You could also draw it in this way, with partial positive charges on each of the carbon atoms. So they are not the same structure. Okay, how to figure out how many hydrogens are attached to a carbon with a charge. So typically what we're doing is we're calculating formal charge. And we're using the formal charge formula to do that. So formal charge equals valence number minus non-bonding electrons and number of bonds. Okay, well, let's say that we have this. So this is a carbocation. And let's say that we want to know how many hydrogens are attached to the carbon with the positive charge. Now, after a while, you're going to see the same pattern over and over and over again. You're not going to need to do this calculation. You're going to see it so many times, you just know it. But before that happens, you may need to back into it, and this is how you would do that. So in this case, what we want to know is how many hydrogens. We know the formal charge, that's 1. It's not a highlighted one, it's just 1. 1. We know the valence number of carbon is 4. And we know that we're subtracting from that non-bonding electrons. Now in the structure, there are 0. And the number of bonds. Well, that's the number that we need to fill in. Now, we know that that number has to be 3 to satisfy the equation. So this must be 3 so that we can satisfy the formal charge equation. 2 of the bonds are shown. So going back to our original structure, I've highlighted in blue the 2 bonds that are shown, which means that there's got to be a third one to the hydrogen that's not shown. So 2 bonds are shown. meaning in this case, there's one bond to hydrogen not shown. Now, as a side note, it's totally okay to draw in the hydrogen. So just because we can omit the hydrogens doesn't mean, especially as you're learning this and getting used to it, doesn't mean that you have to. The allyl cation and patterns like it, again, are typically going to be parts of larger molecules. So let's draw a picture of a more complicated molecule, but again, we're recognizing structural features that allow us to decide whether or not we can draw resonance. Here we have a double bond next to a positive charge. So we have an allyl cation within this molecule. So you can start an arrow at the double bond and point to this bond next door, the one that's associated with the positively charged carbon. And that gets us to this. Let's do another one of these. So again, you have a more complicated structure, but you are looking for the pattern. The pattern is this one, a double bond next to an atom with a positive charge. Move a pair of electrons out of the double bond toward the positive charge into that bond. And so the result will look like this. Okay, so that's the allyl cation. Let's take a look at the allyl anion. An allyl anion, as the name implies, is an allyl group that carries a negative charge. It's an example of a carbanion. Carbanion is a structure that has a carbon that has a negative charge. This is going to show us what to do if we have a structure that has a lone pair next to a double, or remember, a triple bond. So let's draw out an allyl anion. We're going to do this again both ways. The full Lewis structure, and then the skeletal formula. Okay, so here's an allyl anion, lone pair and negative charge on the allylic carbon. What we're going to do here is the following. We're going to start an arrow at the lone pair. Notice that we're not starting an arrow. In fact, I'm going to move my charge out of the way so this doesn't get confusing. Notice that we're not starting the arrow at the charge. The arrows always start at electrons. Whether those are lone pairs or bonding electrons or single electrons, they always start only at electrons. So we're going to start an arrow there and point to this bond right here. That means that we're moving those electrons into a double bond. That would exceed the octet on that central carbon. So a pair of electrons is going to move away. We're going to put it on the carbon on the left. When we do that, the carbon on the left accrues a negative charge. And now it's the middle and right-hand carbons that are involved in the double bond. Let's redraw this using the skeletal format. So starting the arrow at the lone pair, pointing to the bond, and then starting another arrow at the double bond and pointing to the carbon atom on the left. Notice the precise placement of the beginning and ends of the arrows. You can't be sloppy with the arrows. This has to be done in a particular way, which is what I'm showing you. And once again, here, we have what we would consider equivalent contributors. So the pattern with the allyl anion is a lone pair next to a double bond. Lone pair next to double bond. Well, as it turns out, it doesn't matter what the atoms are that are involved in the pattern. It's going to follow the same rule as we just saw. So here's the enolate ion again. Now, a little while ago, we drew resonance for this, but now what we can see is that this is part of a pattern, a lone pair next to a double bond. It's not an allyl pattern because the atoms involved in the double bond are not both carbons, but it's still going to behave in terms of resonance in exactly the same way. Move a pair of electrons in, push electrons out of the double bond and onto the oxygen. That gives us this. Now in this case, this is the major contributor, as we saw before, because the negative charge is on the more electronegative element. I'm going to abbreviate electronegative because that's a long word that I want to write out every time I say it. En. So this is just like allyl anion pattern. So drawing this out, so notice how this corresponds to the structure on the far left. So you have a lone pair next to a double bond, move electrons in, push electrons out of the double bond onto that atom at the top of the structure. And that gives you another contributor. Again, these patterns are showing up, or will show up, in larger, more complex molecules. So let's practice a couple of those moves. Again, when you're looking to assess resonance, first of all, can I draw resonance? I'm hoping that what you're picking up on is the features that you're looking for are typically going to be double and triple bonds and charges. So here we have a double bond, and it happens to be right next to a lone pair. In this case, there's a negative charge associated with it, but there doesn't necessarily have to be, as we'll see. The pattern is always the same. And so by invoking the pattern and applying the pattern of arrows, we get to the structure on the right. Now I'm going to draw a couple of other arrows on that original structure to illustrate a point. So when people are learning how to draw the arrows and this sort of thing, oftentimes they're concerned about doing it exactly the right way, which is a very healthy attitude to have. So what I mean by that is the following. Sometimes I'll get a question, so I drew the arrows the way you see on the screen right now. But someone will ask, well, could I have drawn it, I'm using a different color here, could I have drawn it like that? That is absolutely, totally fine because it's getting you to exactly the same place. So the position on the structure, whether it's on the top of the structure or the bottom of the structure or above the bond or below the bond or outside the ring or inside the ring, where you put the arrow doesn't matter. What matters about the arrow is the precision of where it starts, has to start at electrons, and where it ends. It has to point to where those electrons show up in the next structure. So you have some artistic license. Okay, let's do another one of these. Oops, suddenly drawing green structures. Okay, so let's do this. Okay, so this one, there's no charge. So what's going on? So we have a double bond and an atom directly attached to those double bond carbons has a lone pair on it. So you have lone pair next to double bond. So you do exactly the same thing that you do with the allyl anion. Start at the lone pair, put the lone pair into a double bond, and then break out 2 electrons from the double bond and put those onto the atom. In this case, that gives you a positive charge on the nitrogen and a negative charge on the carbon. So 2 things. First of all, this is not an allyl anion, but it follows the same pattern. Another point that I'd like to make is look at the nitrogen. The nitrogen has a positive charge. Hopefully you're sitting down. Okay? But you don't really need to, because the nitrogen has an octet of electrons. So that positive charge is not something that we want to worry about. The nitrogen has an octet. The positive charge is okay. Remember, you just don't want to have oxygens and nitrogens with positive charges when they don't have octets. That's to be avoided. Okay, let's extrapolate this pattern to some other molecules that we've seen. And those are carboxylic acids and their derivatives. They also follow this same pattern. Now let's start with esters and amides. We'll use those as our examples. So here's a structure of an ester. Now the first thing we need to do is get the lone pairs on there. So how many lone pairs are each of those oxygens going to have? If you said 2, that's excellent. So they each need 2 lone pairs. Okay. So, thinking back to the allyl anion pattern, we recognize that we have a double bond, and right next to the double bond is an atom with a lone pair. That means that we can take that lone pair, move it into a double bond, and pull electrons out of the double bond and put them onto that carbonyl oxygen. The result is the structure that I'm drawing right now to the far right. Okay. So I'm going to redraw this arrow. So the red arrows that I just drew on the curved arrows on the original structure got us to the structure on the right. But there was another move that we could have made. We could have, since there's a carbonyl in this, we could have just done the simple move that we started out with formaldehyde, which is this one. So I'm using a different color to show what we would get to. If we started that way. Now, once we get to that brings up another pattern. Now, we're going to look at this pattern in a few pages, but I can show it to you now. You have an atom with a lone pair next to an atom with a positive charge. So what you would do is just take the lone pair and move it into a double bond, and that actually will get you to the structure on the far upper right. Okay, now, in the last video, we looked at a set of ideas to assess the importance of resonance contributors. So what I would like you to do is pause the video and apply those ideas to these 3 structures and figure out which is the major contributor. Okay, so there's always going to be just the one, or unless you have equivalent contributors that are both major. In this case, there's just one major contributor, so I'd like you to identify it. And then of the other 2 contributors, I'd like you to see if you can figure out which one is the least important contributor, which one's contributing the least to the hybrid. So pause the video and see if you can work through that issue. Okay, so having done that, hopefully what you found was the following. Let's label the structures A, B, and C. A is the major contributor. Now the reasoning for that, remember the octet rule is the first thing we look at, and the octet rule is satisfied for all the atoms that need octets in that structure. So we're good there. We have also minimized formal charge. Say FC for formal charge. So we've minimized formal charge. We don't have any non-zero formal charges, so you can't get more minimal than that. The most minor contributor is structure B. In structure B, carbon lacks an octet. You also have a separation of charge. So it's that lack of an octet on the carbonyl carbon that makes this the most minor contributor. Structure C we'll call minor. And the reason that it gets to be minor and not most minor is because all of its atoms have octets. Now you might be suspicious about that ester oxygen that has the positive charge, but go through and count the electrons around it, and you will find that it has 8. So I'm highlighting them as I count them. So focus on structure C. So we have 2, 4, and then in the double bond, 6, 8. So this structure has all octets on all the atoms, and it does have a separation of charge. Now you might be thinking, well, that's a larger separation of charge than the separation of charge in structure B, and you'd be right. The problem is, in structure B, carbon lacks an octet, so that dings it, if you will. Okay? So it's less important because of that feature. So the separation of charge, even though structure C has a larger separation of charge, the positive and negative are farther away from each other, all the atoms have octets, and so that makes it more important than structure B. Let's do this exercise for the amide. So again, we have to put the lone pairs in. This is good practice. And then we recognize that we have an atom with a lone pair directly adjacent to a double bond. And so we use the same moves that we do for the allyl anion. So what I'm showing you is going to be true for all the carboxylic acid derivatives, carboxylic acids themselves, and really any case where you have a lone pair on an atom that's next to a double or triple bond.